In this presentation, we will summarize some of the factors contributing to increased bromide concentrations in surface drinking water sources. This work was prepared in collaboration with Butts County by researchers at the University of Georgia, with financial support from Butts County and a regional water plan seed grant from the Georgia EPD. Bromine is a chemical element belonging to the highly reactive halogen group, which also includes elements including fluorine, chlorine, and iodine. Halogens are oxidizing agents that form anions by accepting an electron. Bromide is the anion of the element bromine. Since elemental bromide is highly reactive, it does not occur freely in nature, but instead exists as salts or acids. Bromide naturally occurs in the Earth's crust, seawater, salt lakes, and underwater brines. Fossil fuels such as coal also contain varying concentrations of bromide. The highest natural concentrations of bromide are found in seawater, shale geologic formations, and coastal groundwater and soils. In the U.S., inland groundwaters, fresh surface waters, and drinking water sources do not typically have naturally high bromide values. Bromide in itself is not a risk to human or ecosystem health when present in source water. However, during the drinking water decontamination process, bromide reacts with natural organic matter present in source water and chemical disinfectants to create brominated disinfection byproducts, which may pose a significant threat to human health. During the drinking water treatment process, chemical disinfectants are used to remove pathogenic microbes and nuisance metals. Hundreds of species of disinfection byproducts can be produced at various stages of the drinking water disinfection process, and this depends on source water characteristics, disinfectant type, engineering practices, water distribution network characteristics, and the climate. Since the 1970s, when disinfection byproducts, or DPBs, were first discovered in finished drinking water, many toxicological and epidemiological studies have examined the relationship between disinfection byproduct exposure and potential human health consequences. Results from toxicological studies using a variety of in vitro and in vivo methods indicate that many classes of DPBs present human health risks. Elevated bromide in source water is particularly concerning because brominated DPBs have been shown to be more carcinogenic and cytotoxic than their chlorinated analogs. In epidemiological studies, long-term exposure to DPBs has been consistently associated with increased risk of bladder cancer, while acute exposure to DPBs during pregnancy has been inconsistently associated with adverse effects on fertility, pregnancy, and fetal development. Importantly, even a relatively low increase in source water bromide concentrations can shift the species and quality of disinfection byproducts produced during the disinfection products and lead to a greater number of brominated DPBs, escalating the risk of adverse human health effects. Recently, Regali et al. Estimated an increase of bladder cancer associated with elevated source water bromide at concentrations equivalent to those frequently associated with anthropogenic contamination. Historical bromide uses include early photographic development and sedatives in human medicine during the 18th and 19th century. The first significant anthropogenic release of bromide into the environment occurred in the 1920s through 1990s when brominated compounds were added to gasoline to prevent lead deposition in the engine. Engine combustion of the added bromine released methyl bromide gas into the environment. The use of methyl bromide as an agricultural fungicide also represented a significant anthropogenic contribution of bromide until its use was largely phased out in the 2000s. Finally, bromide has been released as a waste product of potassium or potash mining activities and found to elevate surface water bromide concentrations in several European countries. Salt mining is still a major industry in various parts of the world and continues to create water quality issue when brines contaminated with bromide pollute surface waters. Current anthropogenic sources of bromide include energy extraction and utilization, coal-fired power plants, water treatment, flame retardants, pre-planting and post-harvest biocides, agricultural herbicides, municipal waste incinerators, landfill leachate, road deicers, and pharmaceuticals. Elevated levels of bromide in source water leads to higher production of brominated disinfection byproducts following drinking water disinfection. Brominated disinfection byproducts are more carcinogenic than their chlorinated analogs, meaning that there are greater human health risks associated with drinking, food preparation, and bathing with chemically disinfected water. Also, greater source water bromide levels can lead to increased formulation of unregulated DPB classes, including those which may be more harmful than the currently regulated byproducts. Source water bromide concentration is one of the most important DPB formation factors, and elevated bromide can lead to as much as a twofold increase in both regulated and unregulated DPBs. Short-term exposure to high levels of DPBs has been weakly associated with restricted fetal growth, while long-term exposure to DPBs is consistently associated with an increase of urinary bladder cancer. Identifying drivers of increased bromide concentrations in source water is essential because once bromide levels are elevated, there are no practical methods to remove the anion prior to disinfection. Further, there are no practical methods available to reduce the number of brominated DPBs in finished water following drinking water treatment. The best method to control bromide levels in source water and prevent the formation of brominated DPBs in finished drinking water is to regularly monitor bromide levels, and if elevated levels are detected, then identify and stop anthropogenic inputs of bromide.